Welcome to the Joy of Architecture. Today we're taking a deep dive into one of the most critical topics in modern software design: how we break down large systems into smaller, more manageable parts. You've probably heard of microservices, right? But the real challenge for architects is deciding, where exactly to draw the lines. That's really our mission for this deep dive, to kind of extract the most important insights from the world of architectural decomposition and these design patterns for building microservices-based systems. Think of it as a shortcut, maybe, to being truly well-informed on this vital subject.
Exactly. We're going to give you a bit of a strategic guide to designing those service boundaries. We'll move from the foundational concepts right into specific powerful patterns. We'll unpack what they actually mean, their benefits, the trade-offs, because there are always trade-offs, and even show you how they play out in practice with some really great examples.
So if you've ever wondered how giants like Amazon or Netflix manage their massive, constantly evolving platforms without, everything just collapsing.
Which sometimes feels like a miracle.
Right. This is definitely for you. Okay, let's unpack this. Before we jump straight into the patterns themselves, maybe let's set the scene a little. What was the journey that led us here to this microservices era? What problems were we actually trying to solve?
Well, historically, we mostly started with monolithic systems. Just imagine one giant block of code where, well, everything lives together. Any change, no matter how tiny, often meant rebuilding and redeploying that entire block. It was pretty rigid.
Yeah, I remember those days. Really slows things down.
Exactly. That rigidity really hampered how quickly businesses could innovate. Now, service-oriented architecture, SOA, that was a step forward. It aimed for more modularity. But it often introduced its own complexities, heavy middleware, complex integrations.
Right.
So microservices are widely seen as the sort of natural evolution from that, focusing on even smaller, truly independent services. And it's all driven by that persistent business need for, faster innovation and adaptability.
That makes perfect sense. It's really about agility, isn't it? So what are the core principles, the key ideas that really make microservices effective? What makes them tick?
It really boils down to a few key ideas. First, autonomy. Each service operates independently, ideally with its own dedicated team. Then, loose coupling through well-defined APIs. Think of them like clear contracts between services so one can change without necessarily breaking another.
Okay, clear contracts. Important.
Very high cohesion is crucial too. That just means all the elements within a single service are tightly related and serve a single purpose. And critically, each service ideally manages its own data store, embracing what we call decentralized data management.
Right, database per service.
Exactly. They're also typically organized around specific business capabilities, designed to handle failures gracefully because, let's face it, in distributed systems, things will fail.
Oh, absolutely. Murphy's Law.
Definitely. And they rely heavily on infrastructure automation, like using containers and CI/CD for rapid, reliable deployments.
Okay, so they promise a lot of upside. Agility, independent teams, rapid deployment. Sounds great. But, every silver lining has a cloud, right? What are the real pain points, the big headaches, that architects need to brace for when they adopt these distributed systems?
Ah, yes. You've hit on the crucial flip side. They certainly amplify complexity. I mean, network latency suddenly becomes a primary concern. Services are talking over the wire, not just within a single process like in a monolith.
Yeah, that network call isn't free.
Not at all. Then there's the, frankly, nightmare of tracing a request across dozens of services when something goes wrong. Debugging gets way harder. And the risk of cascading failures, if one service goes down, it can potentially take others with it if you're not careful.
Right, the domino effect.
Exactly. And maybe the biggest challenge is data consistency.
Yeah.
You often can't achieve instant perfect consistency everywhere across all those separate databases.
Yeah.
So we often have to embrace eventual consistency, meaning data might take a moment to update everywhere, but it will become consistent over time.
Okay, eventual consistency. That requires a shift in thinking.
It does. And we also rely on patterns like Saga, which helps coordinate complex business processes across multiple services when a single atomic transaction just isn't possible. It's really about managing complexity, not trying to eliminate it. That's the key mindset shift.
That distinction is so important. Managing complexity, not eliminating it. Okay, let's move to our first major pattern then. Decompose by business capability. If I'm trying to wrap my head around it, is it basically about aligning our tech, our services, directly with the core functions that make the business money?
Exactly, you nailed it. This pattern is all about breaking down an application into services based on the distinct functions a business performs to create value. Think order management, product catalog, or payment processing. Each service encapsulates all the logic and data for that specific business function.
Okay.
It tends to work best for organizations that have a really deep understanding of their business units. Because these core capabilities, they tend to be more enduring than the specific technical implementations.
Right, the business changes slower than the tech sometimes.
Often, yes. So it provides a more stable architectural foundation over time.
That makes sense. It sounds like a powerful way to foster that team autonomy we talked about.
So what are the biggest upsides and maybe the trickiest downsides of going this route?
Okay, at its core, the major benefit is definitely that team autonomy and a stable architecture. Teams own an entire business function end to end. That often leads to faster development and deployment cycles. And like we just said, because business capabilities change less often than technical details, your architecture stays more stable. That's invaluable.
Yeah, stability is good.
You also get high cohesion within services and loose coupling between them. It aligns really well with something called the common closure principle, basically. If you need to change something related to orders, you ideally only touch the order management service.
Got it. Keep changes contained.
Exactly. The trickiest part, though, is the difficulty in accurately identifying those capabilities in the first place. It requires real business insight.
So if you get the boundaries wrong, you can end up with what we sometimes call a distributed monolith. Looks like microservices, but they're all tangled up. You'll also face those data consistency challenges across services, which need careful management, like eventual consistency patterns. And there's just an increased overall operational complexity from managing many distributed services, especially around things like monitoring and security.
Right. More moving parts to watch. It sounds like a really strong pattern if you get those boundaries right. Where have you seen this decomposed by business capability pattern truly shine in the real world? Any big examples?
Oh, absolutely. There are some fantastic examples. Amazon is probably the classic case. There are services for personalization, search, recommendations, even the complex systems within their fulfillment centers for inventory and shipments. They're all decomposed by capability.
Wow.
That's how they manage, supposedly, an astounding 50 million deployments a year.
50 million. That's incredible.
It is. Spotify is another great example. They use hundreds of single-purpose microservices for things like playlist management and personalized recommendations. This allows them to contain issues and continuously refine features independently. And Netflix, of course, a real pioneer in this space. They famously decomposed their monolith into, I think it's over 700 microservices now for things like managing watch shows, payments, viewing history. This drastically improved their availability and scalability, especially during peak viewing times. They could scale just the customer profile service, for instance.
Okay, so the giants use it effectively. Now, when an architect is, say, whiteboarding this pattern, sketching it out, what are the key visual elements they'd be drawing? How does it look different, maybe?
Great question. Visually, you typically represent the microservices as distinct boxes, clearly labeled with their business capability like order management service or inventory service. A crucial element is the API gateway. You'd show that as the single entry point, routing external requests to the correct service.
So one door in.
Pretty much. And importantly, each service box would usually have its own dedicated database shown inside its boundary. That visually emphasizes the decentralized data ownership.
Right. No shared database icons spanning multiple services.
Ideally not. Then you'd have arrows showing the communication paths. These might indicate synchronous API calls, maybe REST, or perhaps asynchronous message queues connecting to a shared event bus. These diagrams really help visualize how those business functions are isolated, yet still collaborate when needed.
Okay, thinking about actually implementing this, bringing it to life, what are the most crucial design choices an architect or a team needs to make?
Number one, I'd say, is team structure. You really want to align your teams directly to these business capabilities, often as small, cross-functional, two-pizza teams, 6 to 8 people max.
The Amazon model.
Exactly. With end-to-end ownership. For communication paths, the advice is generally to prioritize asynchronous messaging using tools like Kafka or maybe AWS SQRSI. This promotes decoupling and resilience. Synchronous calls like REST or gRPC can be used, sure, but where absolutely necessary and always with very clear, stable API contracts.
Right. Don't make everything synchronous.
Please don't. And for data ownership, that database per service rule is pretty key for autonomy, which again means you'll definitely be dealing with eventual consistency, probably using patterns like the Saga pattern we mentioned.
Okay, makes sense. And on the flip side, what are the classic pitfalls or, anti-patterns that teams often stumble into when trying to apply this decomposition by business capability?
Yeah, there are a few big ones to watch out for. First, microliths. It's a slightly confusing term, but imagine you've broken down your system. But a single external request still requires calls between multiple of these microservices before it can complete. Often, they try to avoid this by using temporally decoupled data reconciliation, basically, updating data later via events. It looks like microservices, but the workflow is still tightly bound. It can become a distributed mess if you're not careful.
Ah, so it looks decomposed, but it's still acting like a monolith internally for certain requests.
Kind of, yeah. Second, and maybe more common, is the distributed monolith.
Yeah.
This happens when your services remain tightly coupled despite being separated. Maybe they share a database secretly, or there's excessive synchronous communication back and forth.
The chatty services problem.
Exactly. If your team consistently needs to coordinate changes across, say, 8 different services, just to add a simple new field to a user profile, you've probably built a distributed monolith. And trust me, they often combine the worst aspects of both monoliths and microservices.
Ouch. Sounds painful.
It is. Finally, there's premature decomposition, sometimes called nanoservices. This is where you break things down too much, way too fine-grained. You end up with massive operational overhead managing hundreds of tiny services, super high communication costs between them, and debugging becomes an absolute nightmare. Like, imagine individual tiny services for user achievements, user preferences, and user friends, each with its own deployment pipeline.
Yeah, that sounds like overkill. Way too complex.
It usually is. You need to find the right balance.
Finding that just right granularity. Okay, so we've discussed breaking things down by business capability. Now, let's pivot to our second pattern. Decomposition by subdomain, which you mentioned, is often linked with domain-driven design, or DDD. How does this differ, and why is DDD relevant here?
Right. So decomposition by subdomain drills even deeper into the business logic and structure. It breaks down an application based on distinct subdomains. Each subdomain represents a specific area of the business with its own unique language, what DDD calls the ubiquitous language, and its own business rules.
Okay, so more focus on the language and rules of a specific business area.
Precisely. Microservices then align with what DDD defines as a bounded context. This is a really key concept. It's the explicit boundary within which a particular domain model, a particular set of rules and language, is consistent and valid.
Bounded context, got it.
And DDD helps classify these subdomains. You have your core subdomain that's your unique business differentiator, the secret sauce. Then supporting subdomains necessary for operations but maybe not unique to you. And generic subdomains, things like authentication or email sending, often solved with off-the-shelf solutions.
Okay, core, supporting generic. That helps categorize things.
It does. This pattern is incredibly effective for really complex applications where understanding the domain is paramount. It's also great for incrementally modernizing monoliths, where you can start to identify these clear business boundaries.
So what's the main draw here? It sounds conceptually similar in some ways to business capabilities focusing on the business side.
They are related, absolutely. But DDD provides a much more structured, rigorous methodology for actually uncovering and defining those boundaries based on the domain logic and language. The main draws are, again, a potentially very stable architecture and truly autonomous development teams, because the decomposition is rooted in that deep domain understanding. This usually leads to highly cohesive and loosely coupled services with strong conceptual integrity. That really improves maintainability and scalability in the long run.
But the trade-offs, still challenging.
Definitely. The primary challenge is the difficulty in identifying those subdomains and bounded contexts accurately. It requires significant domain expertise, collaboration between developer and business experts, and often iterative analysis. It's not something you just guess.
Right, it takes real effort.
It does. It can also lead to too many services if you're not careful about the granularity of your bounded contexts. And just like before, data consistency across different bounded contexts remains complex. You're back to eventual consistency, saga patterns, and needing careful coordination. There's also an initial learning curve for the team to really grasp DDD concepts.
Makes sense. Are there companies using this DDD approach, maybe even if they don't explicitly label it subdomain decomposition?
Oh, absolutely. Many large, complex organizations implicitly leverage DDD principles, even if they don't use all the formal terminology. Netflix's decomposition, for example, into user management, content catalog recommendations, playback these align very strongly with what you'd identify as distinct subdomains and bounded contexts.
Right, those feel like separate worlds within Netflix.
They do. Amazon's famous two-pizza team rule and their decentralized service ownership often mirrors DDD principles in practice. Those small, autonomous teams naturally gravitate towards owning distinct business domains or subdomains. Uber explicitly talks about using a domain-oriented microservice architecture. Their ride service, driver service, payment service. These are essentially subdomains mapped to services.
Okay, so it's definitely used in practice at scale. Now, thinking visually again, when architects are diagramming this, how does a diagram for decomposition by subdomain using DDD look different from the business capability one? What's unique?
The key concept to visualize here are the bounded contexts themselves. You draw them as clear containers, perhaps with a distinct border style, showing which microservices belong inside that context. You might also explicitly draw context map diagrams. These are specific DDD diagrams that show the relationships and, importantly, the integration patterns between different bounded contexts.
Ah, so how the contexts interact.
Exactly. Are they using an anti-corruption layer? Is there a shared kernel? Are they communicating via published domain events? The context map clarifies those strategic integration choices. You still show the microservices within their context, their dedicated data stores, and communication paths, arrows. But the emphasis is really on those explicit boundaries and the relationships between them. For instance, a sales-bounded context communicating with a shipping-bounded context via asynchronous domain events.
That focus on the context boundaries and interactions seems key. What are the crucial design points then to make this DDD approach work well in practice?
Again, team structure is vital. Ideally, teams should be organized around specific domains or subdomains, fostering that deep domain expertise and end-to-end ownership within the bounded context.
Domain experts embedded in the team.
Ideally, yes, or very close collaboration. For communication paths, explicit API contracts defined using the ubiquitous language of the domain are vital. Asynchronous communication, often via domain events published on a message bus, is frequently preferred for coordinating actions across bounded contexts, maintaining that loose coupling. API gateways are still used for external entry points, and for data ownership, it's strict. Each microservice, representing its bounded context or part of it, owns its data and its database schema. Direct database joins across service boundaries are a major anti-pattern here. Eventual consistency is the norm between contexts.
Okay, strict data isolation per context. And the anti-patterns. What common mistakes really undermine the value of DDD decomposition?
One really major one is the anemic domain model. This is when your core domain objects the things representing your business concepts like order or customer end up just being simple data bags with getters and setters. All the actual business logic, the rules, get scattered in separate service or manager classes outside the domain objects themselves. This leads to low cohesion and high coupling, the opposite of what DDD aims for. You want to encapsulate business logic within your domain objects.
Keep the logic with the data it operates on.
Exactly. Another classic is the God object or God class. A single service or class that tries to do way too much, knows about too many other things, and becomes a central bottleneck or a big ball of mud. You have to adhere strictly to the single responsibility principle and keep your bounded contexts focused. The distributed monolith is, of course, still a threat here if you get the boundaries wrong or a couple of contexts too tightly, perhaps through shared databases or excessive synchronous calls.
Always lurking.
Always. And finally, ignoring the ubiquitous language. If the team doesn't actively develop and use a shared, precise language based on the domain, misunderstandings creep in, requirements get misinterpreted, and your service boundaries might not reflect the actual domain divisions.
That shared language seems fundamental. Okay, we've covered breaking things down by business capability and by domain using DDD. Our third pattern is the self-contained system, or SCS. Now, that name immediately makes me wonder, is it almost like a mini monolith, but just for a specific business area, maybe even including its own UI? That sounds quite different from the pure microservice idea we've been discussing.
That's a very perceptive way to put it. Yes, a key differentiator of an STS is exactly that vertical slice. It's conceived as an autonomous web application or business unit encompassing everything needed to deliver a complete feature or domain functionality. That typically includes its own user interface, its own business logic, and its own dedicated data storage. It's truly a complete, independent, deployable unit.
A whole vertical slice, UI and all? Okay.
Key characteristics include that completeness, strong autonomy, and ideally minimal synchronous communication between different SCSs. Interaction often happens via UI-level integration, like simple hyperlinks or asynchronous events, and strict data isolation is paramount.
Interesting. So where would this be most suitable?
It's great for modeling very distinct business domains where interaction is naturally limited. It's fantastic when maximizing team autonomy is the absolute top priority. And it's particularly well suited for incremental modernization of large legacy systems. You can carve off vertical slices as SCSs. It kind of addresses situations where going fully microservices might feel too complex or fragmented.
Right, a sort of middle ground maybe. So beyond that strong team autonomy, what are the unique benefits and, importantly, the trade-offs of this SCS approach compared to the others we've discussed?
The main benefits really stem from that independence. You get simplified deployment. Each SCS is deployed entirely on its own schedule. You get enhanced fault isolation. If one SCS fails, it's less likely to impact others directly. This leads to extremely fast time to market for features within an SCS boundary. It also allows for incredible technological flexibility. Different SCSs can potentially use entirely different tech stacks if desired.
Wow, okay. That's flexibility, but the downsides.
The trade-offs are significant too. There's a real potential for duplication of logic or even UI components across different SCSs if you're not careful with shared libraries or design systems. Data consistency challenges are often even more pronounced because integration is minimal, relying heavily on eventual consistency or sometimes data replication for read-only purposes. There's also the operational overhead of managing multiple complete independent systems, monitoring security infrastructure for each one. And maintaining a consistent user experience can be tricky across separate UIs unless you invest heavily in shared design systems and front-end integration patterns.
That UX consistency sounds like a big one to manage. Any good examples of companies using this, maybe without explicitly calling it SCS? Where has this vertical slice idea worked?
A really compelling example I read about involved a wholesale company's ERP modernization. They had this massive 20-year-old monolithic ERP system. They decided to migrate it incrementally by building out several self-contained systems. Each new SES handled a specific domain like ordering or inventory, and crucially had its own UI, its own backend logic, and its own database schema.
So they sliced the monolith vertically.
Exactly. They tied these SCSs together using single sign-on, SSO, for authentication and a shared design system for UI consistency. Communication between them was primarily done via asynchronous data replication for shared read data and simple UI links or redirects. This allowed them to completely avoid a risky big bang rewrite.
That sounds very practical for legacy modernization.
It is. You could also argue that Amazon's checkout process implicitly uses SCS principles. Think about the user journey. Moving from your shopping cart to selecting shipping to entering payment details, it often feels like you're interacting with separate specialized systems that are seamlessly integrated. They achieve that scale and iteration speed partly through this kind of minimal communication and strong boundaries, likely tied together with SSO.
Interesting perspective on Amazon's checkout. Okay, and when you're drawing this out, how do you visualize an SCS compared to a microservice diagram?
You typically draw each SES as a much larger, distinct container or box compared to a single microservice. Inside that box, you'd clearly indicate its internal components, the UI layer, the business logic layer, and its dedicated data storage. The diagram really needs to emphasize that vertical slicing concept.
So you see the layers within the SCS box.
Precisely. Communication between SCSs is shown differently too. You'd emphasize UI-driven integration, maybe arrows representing hyperlinks or redirects between the UI layers of different SCSs. You'd also show message queues or event buses for any asynchronous data exchange needed. Synchronous API calls between SCSs would be shown, but the implication is that these should be minimal and stable. Shared components like an SSO system or a central design system library might also be shown outside the SCSs, indicating how consistency is maintained across them.
Got it. The visualization really highlights the self-contained nature. What are the crucial design points, the key considerations for making SCS work well?
Number one is team structure. You absolutely need dedicated, full-stack, cross-functional teams for each SCS. They need complete end-to-end ownership of their vertical slice. Small, empowered teams are key.
Full stack ownership per SCS.
Yes. Regarding communication paths, the strong recommendation is to prioritize asynchronous communication for decoupling if backend integration is needed at all. UI-driven integration via hyperlinks or redirects is a core tenet for navigating between functionalities offered by different SCSs. If you must have synchronous APIs between SCSs, keep them minimal and incredibly stable. And for data ownership, it's non-negotiable. Independent data storage for each SCS. No direct database joins between SCSs. Data needed across boundaries might be replicated asynchronously for read purposes. You have to fully expect and design for eventual consistency across the different SCSs.
Okay, strong boundaries, async or UI integration, independent data. What are the specific anti-patterns to watch out for when building self-contained systems? Where does it go wrong?
Well, believe it or not, the distributed monolith can still rear its ugly head even with SES. If your supposedly independent SESs become tightly coupled through too many synchronous API calls back and forth, or maybe they sneakily share database tables or have brittle interdependent deployment pipelines, you lose that autonomy.
Oh, coupling creeps back in.
It can. Another anti-pattern is directly sharing business logic code, like common libraries containing core rules, between SCSs. This creates tight coupling at the code level and undermines their ability to evolve independently. Share carefully curated data contracts or use events, not complex logic libraries. Making SCSs overly granular is another issue. If you slice things too thinly, you end up with too many independent units to manage, monitor, and deploy, increasing operational overhead unnecessarily. It negates some of the simplicity benefits.
Finding that right slice size again.
Exactly. And a very common failure mode is ignoring user experience consistency. If you don't invest in and enforce a unified design system, shared UI components, where appropriate, and seamless navigation like SSO, you end up with a fragmented, jarring user experience as users move between different SCSs. It feels like using different applications cobbled together.
That UX point seems critical for SCS success. Okay, we've talked a lot about decomposing systems into various types of services, but let's take a step back. How do these newer microservice and SCS approaches really stack up against a more traditional N-tier architecture? For someone trying to decide which path to take, what are the core trade-offs?
That's a really good question, because it's crucial to remember the choice isn't about which one is inherently better, but which one is appropriate for the specific context, the application, the team, the business needs. So let's define N-tier architecture first. Typically, it separates an application into distinct logical layers, usually a presentation layer, the UI, an application or business logic layer, and a data layer. Components within a given tier are often quite tightly integrated, and the application is usually deployed as a single large unit or perhaps a few closely coupled units. You visualize it as a vertical stack.
Right, the classic three tiers: presentation, logic, data.
Exactly, the benefits. It's generally simpler, especially for smaller applications. There's lower initial development and operational overhead compared to distributed systems. Communication within the layers is usually direct, in-process calls, so latency isn't typically a major issue. Sometimes scaling is easier if the entire application needs to scale uniformly. And debugging can be simpler because everything's more centralized. It's often suitable for smaller teams working on less complex projects with stable requirements.
Okay, simpler, lower overhead initially. What are the downsides?
The main trade-offs for N-tier are tight coupling between the layers. A change in the data layer might ripple up and force changes in the business logic and even presentation layers. Scalability can be a limitation. If only one part of the business logic needs more resources, you often have to scale the entire application, which is inefficient. There's often technology lock-in. It's harder to introduce different programming languages or data stores for different parts of the application. Development cycles for large N-tier apps can become slow because the whole thing often needs to be rebuilt and redeployed together. And fault isolation is reduced. A failure in one component within a layer can potentially bring down the entire application or tier.
Okay, so N-tier is simpler initially, but can become rigid and hard to scale or change later. How does that compare directly to the microservices architecture we've been discussing?
Well, microservices architecture, as we've established, is that collection of small, independent, loosely coupled services, each focused on a single business capability. They run in their own processes, communicate via lightweight APIs or message queues, and typically own their data store. The benefits are significant. Independent scalability and flexibility. You scale only the services that need it. Rapid development and deployment, because teams can work and deploy independently. Enhanced resilience and fault isolation. One service failing shouldn't cascade and bring down everything else if designed well. Technology diversity. Different services can use different technologies best suited for their job. And easier maintenance due to smaller, focused code bases supporting those autonomous teams.
That sounds like a lot of advantages for complex systems, but the trade-offs must be there too.
Oh, definitely. The trade-offs for microservices are primarily around increased complexity. You're dealing with a distributed system now. That means complexity in deployment, monitoring, and debugging across multiple services. There's higher operational overhead. You need infrastructure for things like service discovery, API gateways, distributed tracing, robust monitoring. Data consistency challenges are inherent due to that decentralized data ownership. You have all those intrinsic distributed system challenges like network latency, partial failures, the need for fault tolerance mechanisms like circuit breakers. Refactoring across service boundaries becomes much harder because you have to manage API versioning and backward compatibility. And often, there's a higher initial cost and effort to set up the infrastructure and processes needed for microservices compared to starting with a monolith.
So much more flexible and scalable, but brings a whole new level of operational complexity and distributed systems challenges.
Exactly. So the bottom line is, for small applications or projects with very stable requirements and maybe smaller co-located teams, N-tier might be perfectly adequate and much simpler to manage. But for large, complex systems, applications experiencing high traffic, systems requiring rapid innovation and evolution, or systems built by multiple distributed teams, microservices, or patterns like SCS, provide a more flexible, scalable, and resilient foundation despite the added complexity. You choose the architecture that fits the problem.
That clarity on when to use which approach is incredibly valuable. Now, this all sounds great for new projects, greenfield development, but as we know, many organizations aren't starting from scratch. They have these large existing monolithic applications. How do they realistically get from that monolith to a more modern service-based architecture without attempting a terrifying Big Bang rewrite that risks the entire business?
The million-dollar question for many companies. That's precisely where the Strangler Fig pattern comes into play. It was famously named by Martin Fowler. The analogy is inspired by certain types of fig vines in nature that grow around a host tree. They start small, gradually grow larger, put down roots, and eventually the vine completely envelops and effectively replaces, or strangles, the original host tree, which then dies away inside.
Wow, quite a vivid analogy.
It is, and it maps really well to software modernization. With the Strangler Fig pattern, you gradually replace parts of your legacy monolith with new microservices, piece by piece. You build the new functionality as services around the old system. Crucially, the monolith remains fully operational during this process. You route traffic incrementally to the new services as they become ready. Over time, the new services strangle the old functionality until eventually the monolith or parts of it can be retired.
Okay, so building the new around the old and slowly redirecting traffic. When is this pattern most applicable?
It's incredibly applicable and often the recommended approach. When a big bang rewrite trying to replace the entire monolith in one go is deemed too risky or too expensive, which is often the case. It's essential when continuous business operation is a must. You can't afford significant downtime. It's great when you still need to develop and release new features while the modernization is ongoing. And fundamentally, it's about reducing risk through incremental change.
The Strangler Fig sounds like almost the perfect solution for modernizing these old monoliths, no big bang rewrite, reduced risk, continuous operation. It almost sounds too good to be true, though. What are the common hidden challenges or the areas where teams really struggle when trying to implement this seemingly elegant approach?
You're absolutely right to be cautious. While the benefits are compelling, definitely reduced risk compared to a big bang, minimal business disruption if done well, faster time to value for the new features deployed as services, flexibility, continuous learning for the teams, and easier rollbacks if a new service has issues. The actual implementation has some serious challenges. Probably the biggest one is the complex coexistence management. You have the old monoliths and the new services running side by side, needing to communicate, often needing to share or synchronize data for a period. Managing this interface and the data consistency during the transition is far from trivial.
Right, that inter-system communication sounds tricky.
It really can be. There's also significant incremental refactoring overhead. You often need to modify the monolith itself to expose APIs or events that the new services can consume, or to allow the facade layer to intercept calls correctly. Finding and untangling hidden dependencies within the monolith can quickly turn into archaeological expeditions. Things you thought were separate are actually tightly coupled deep inside. Data migration issues are another huge hurdle deciding on the strategy. For example, duplicate data temporarily use change data capture (ETL) processes, ensuring consistency during the migration, and eventually transferring data ownership cleanly. And sometimes there can be performance overheads introduced by the network calls between the facade, the new services, and the monolith, which need careful monitoring and optimization. Plus, don't underestimate the organizational challenges coordinating teams working on both the old and new systems.
Okay, so definitely not a silver bullet. Requires careful planning and execution. So what are the practical steps involved? How do you actually do this incremental strangling in practice?
It usually follows a fairly logical sequence. First, You need to identify and isolate components within the monolith. Analyze the existing system, perhaps using DDD concepts to find bounded context, or identify clear business capabilities that are suitable candidates for extraction. You need to prioritize which parts to migrate first, typically starting small, with less complex or less critical functionalities to build momentum and learn.
Start small, learn fast.
Exactly. Step 2 is to build the Strangler facade. This is a critical piece, an intermediary layer, often implemented using an API gateway or a reverse proxy. This facade intercepts all incoming requests that would normally go to the monolith. Initially, it just passes everything through. Then you develop microservices for the functionality you're extracting. Build these new services following best practices, independent deployment, clear APIs, etc.
The new shiny service.
Right. Alongside this, you need to plan and execute your data migration and management strategy. How will the new service get the data it needs? Will you duplicate data, use event sourcing, CDC? How will you eventually transfer ownership from the monolithic database to the new services database? This needs careful thought up front. Now comes the core loop, incremental replacement. You move functionality piece by piece. You update the routing rules in your Strangler facade to redirect specific requests, for example, request to AP orders, to the new microservice instead of the monolith. You might use feature flags to control the rollout, sending maybe 10% of traffic first, then 50%, then 100%.
Gradual redirection via the facade.
Precisely. Throughout this, testing and quality assurance are absolutely crucial. You need rigorous testing of the new services and their integration with the facade and potentially the remaining monolith. Robust monitoring, centralized logging, and distributed tracing become essential to understand what's happening in this hybrid system. You also need continuous deployment and integration pipelines set up specifically for your new services so they can be deployed independently and frequently. Then, as functions are fully migrated and stable, you begin the iterative decommissioning phase. You can start removing the now unused code and potentially even database tables from the monolith. This is where you finally start shrinking the old system. Eventually, you might decouple the monolithic database entirely if all functionality moves out.
And presumably some optimization at the end.
Yes. The final phase involves finishing and optimization, continuous performance tuning of the new services and the facade, refactoring based on lessons learned, ensuring documentation is up to date, and maybe tackling the next piece of the monolith to strangle.
That's a very clear step-by-step process. Are there well-known companies, besides the ERP example, that have successfully used the Strangler Fig pattern?
Oh yes, several major ones. Amazon, as mentioned before, famously used principles aligned with the Strangler Fig to modernize its massive retail platform over many years without significant downtime. They built new service capabilities around the old core. Netflix's multi-year iterative decomposition of their original monolith into hundreds of microservices also perfectly aligns with the Strangler Fig philosophy, even if they didn't explicitly call it that initially. The Commonwealth Bank of Australia is often cited as a case study where they utilized the Strangler pattern effectively to modernize their core banking platform, a notoriously difficult undertaking. There are reports from companies like Altexsoft implementing it for a complex 20-year-old legacy property management system. And even large travel tech companies like Sabre and Amadeus have been gradually migrating functionality from older SOAP-based APIs to newer REST-based microservices, which is essentially a form of the Strangler Fig pattern applied at the API level. It's a proven strategy for tackling large-scale legacy modernization.
Wow. Okay, what an incredible exploration of system decomposition. We've really peeled back so many layers today, haven't we? From the whole evolution towards microservices to the real nitty-gritty of specific decomposition patterns, like by business capability, subdomain with DDD, self-contained systems.
And comparing them to N-tier.
Right, and even diving into how to gracefully transition from a monolith using that Strangler Fig pattern. It's been a lot to cover.
It has. But I think the fundamental takeaway, if there's one thing to remember, is that effective service boundary design isn't just a technical exercise. It's not just about drawing boxes on a diagram. It's really an intricate interplay between core software design principles like striving for high cohesion within your services and loose coupling between them, and having a deep, genuine understanding of your business domain. What does the business actually do?
So business understanding is paramount.
Absolutely. And aligning your architecture with your organizational structure, how your teams are set up, is key. Truly leveraging Conway's law, the idea that your system architecture will eventually mirror your communication structure, can work for you if you structure teams around service boundaries, enabling that autonomy we kept mentioning. What's also truly fascinating and maybe counterintuitive for some, is that architects in this space must embrace the inherent complexity of distributed systems. You can't wish it away or pretend it doesn't exist.
Right, you said manage it, not eliminate it.
Exactly. You have to design for failure, assume things will break, design for resilience, build systems that can gracefully handle partial failures and recover. That mindset shift is critical.
So, thinking about our listeners, what does this all mean for you? I guess it means really thinking hard about choosing the right granularity for your services, not too big, not too small.
Goldilocks services.
Yes. Prioritizing that business understanding, maybe over just chasing the latest technical trend because it sounds cool. And always thinking incrementally, especially when you're migrating existing systems. Don't try to boil the ocean. It's about building systems that are future-proof, systems that can adapt as the business adapts. For us here on the show, it's really about trying to make sense of all this information overload out there, maybe giving you those aha moments, and hopefully providing a bit of a shortcut to being really well informed on these complex topics.
And perhaps this raises an important question for you, the listener, to mull over after this. Thinking about the systems you work on or design, how will these patterns decomposing by capability, by subdomain, SCS, or even the Strangler Fig reshape your approach? Whether you're building something brand new or modernizing something old, what boundary might you draw first and why?
That's a great question to leave people with. We really hope you've enjoyed this deep dive into the joy of architecture. If you found this insightful, please make sure to subscribe to The Joy of Architecture wherever you get your podcasts for more explorations into the fascinating world of software design and building. Until next time.